right, good morning. It's a kind of a funny transition. I feel like just haven't really seen your facial expressions before to a large extent. It's kind of funny to transition midday yesterday or on Tuesday. Um, okay, so before I get started, so today we're going to go over secondary treatment, kind of activated sludge processes, specifically in some of the microbiology and modeling that. But I wanted to get a little bit of your feedback. So by show of hands, um, let me explain the question first. I'm thinking about, instead of going over the previous exam on Tuesday this coming week, continuing with normal lecture material and putting that off until the exam review day and going through so that I can get through more of the homework related content for you. Realize we have like this lecture and then 3 more for the semester. That's it. That's kind of crazy. So I just feel like everything's behind this semester. So, okay, by show of hands, would you rather that option that I just said to delay going over it in favor of getting more course material covered before the break? It'll be online for you if you're going to just travel and then deal with it there. So show of hands, yes, that sounds good. Okay, so that'll be my plan then. It'll be on the exam review day. I'll be going over the homework and that exam, so it'll be a little bit rushed, but I can always follow up a little bit if needed. Yeah. Partly. So about half of it's going to be on the material we're covering now. Given that we haven't spent a whole lot of time on this section, it kind of makes sense, but a lot of the topics are building anyway. Even in our slide right here, we see this clarifier, that's sedimentation. We can kind of connect those, for example, into the processes. Okay. Any other questions or concerns? All right. So today we're talking about secondary treatment, primary being, kind of the screen, bar rack, that kind of stuff. The first sedimentation basin. That gets out some of the stuff, and that'll typically reduce the BOD by maybe 30 or 40%, something like that. It actually does a decent job because you're settling out a lot of solids that would otherwise be a problem, or have a lot of organics associated. But really, the bulk of the work is being done by the aeration basin, activated sludge. So, for our aeration basin, really what we want to know is how many bacteria are there, how quickly are they consuming the food, and what impact does it have on their food, which is the waste that we're trying to treat. So that's sort of the concept, and then we want to collect any bacteria that we just produced with this process and capture them before those bacteria discharge into the rivers, waters, wherever we're sending it, because we don't want to contaminate the outgoing water. We also want to make use of this sludge that's going to accumulate and recycle a portion of it so that we can keep the right bacteria and the right amount of bacteria happily growing in our aeration basin. So we need some sort of a seed stock to keep the process going. Ideally, this clarifier will work perfectly and it'll remove all the bacteria that we grew. We measure typically on a mass basis. I'll explain that in a minute. For the bacteria, it's kind of like an estimation. So this clarifier, we say that it removes, it's perfect at removing the bacteria. That's a typical assumption, meaning our bacteria in the effluent, the secondary effluent here, should be 0. That's by mass, and so maybe that kind of makes sense. If you weigh the amount of particles you can collect there, most of it has settled. But in reality, of course, there's free-floating bacteria everywhere in the solution. So we're still going to need a disinfectant, right? That's not a perfect removal in reality, but in terms of the mass the bacteria associated with mass particles that you can settle out, it's pretty good. Another thing to consider, by the way, when we're talking about these types of systems, a lot of times you'll see this, the primary, the secondary, and maybe even a tertiary step. And so the primary effluent, you think effluent, you think, oh, this is discharging. Well, if you see this written here, it's the primary effluent, meaning it's flowing away from the primary process into the secondary process. So this is a primary effluent or secondary influent. My brain decided that it wanted to write influent, so I wrote an I. Okay. So two names for the same thing, right? Okay. So that's kind of the scope of secondary treatment. Last thing I want to highlight here on a kind of a process design scale is the role of controlling the waste activated sludge line. So WAS, it's a waste activated sludge. That's really important because that's how much sludge we're sending to the landfill. That's going to control, if we waste more, then we're recycling less. Because we're going to be accumulating some set amount in our clarifier. So if we are sending most of that to solid waste, that means we're not recycling much. That changes how much bacteria are effectively going back into the tank, and that changes what we'll learn as the solid retention time. How long do the solid particles, the bacteria associated with them, stay within the system? That will change even if the hydraulic retention time doesn't have a net change by recycling some water. Okay, and you'll notice this drawing is also has a control volume, the dashed line, outside of the clarifier and outside of that recycle line. So the hydraulic retention time in this control volume is what we're going to care about. One more assumption here, that since we're not feeding oxygen to the clarifier, we assume that there's not really much bacterial digestion occurring in there. And then if we make all those assumptions, and we'll kind of get to the math in a minute, then really our process is here. That's all that really matters. And our hydraulic retention time, it really just matters that specific volume and the flow rates going in and out. Okay, so a lot of stuff that I said up front we'll get to as we go through it. A couple pieces of terminology, just have it here for you. Waste activated sludge, WAS, that's the microbe sludge that we collect. Our aeration system is typically going to be a CSTR. Should be fairly obvious. All that bubbling mixes quite a bit. The wastewater strength, if you see a problem or see in the industry somebody's talking about the strength of wastewater, really what we're referring to is that amount of food in it, the BOD, which is typically going to be between 60 and 500 milligrams of BOD per liter. That's sort of a general range. BOD, as a reminder, that's the mass of oxygen that will be demanded by bacteria in order to consume this stuff. So it's technically a measurement of oxygen, but it's in relevance to this waste that's in the water. Because that waste will be food for the microbes, therefore the microbes will eat it and then consume oxygen doing respiration. So it's a measure of waste in oxygen units. Okay, last term here then would be volatile suspended solids. This is our method of measuring the mass of bacteria. It'd be very hard to weigh an individual bacterial cell. And there comes the question, do you dry it first? And once you dry it, it's kind of not going to be there hardly anymore. So there's the way we do this then is we take a filter or a sample of water and we dry it completely. We weigh the filter or maybe a crucible first, dry it completely. So whatever amount of water we put in there or filter through, we're going to have some particles and we're going to drive off all the water. So we evaporate everything and then we weigh it. That'll give us our total solids. So we'll get a total suspended solids TSS filter. We have that weight, and then We burn that at 500 degrees Celsius. It's like 800 Fahrenheit or so. So really hot. It drives off anything that could burn, oxidize, volatilize away. And we let that happen for a couple hours, and then we weigh it again. So anything that volatilized gets categorized then as volatile suspended solids. So we weigh the difference between when we had just the total solids and then after burning it away. We're left with some ash. What we cared about is what escaped, right? So the difference there is what escaped. And so TSS, the mass, we'll say mass, TSS minus mass remaining equals VSS. And that's just a very simple, straightforward, and handy way to measure the amount of organic material in our sample. And essentially, we count that as our bacterial mass. It's not a perfect measurement, obviously. There's other organics in there that are not bacteria, but it's handy. It gives a good estimation for wastewater operation purposes. All right, so I mentioned primary treatment gets rid of a little bit of BOD, maybe 20 to 30% of what's coming in, something like that. And then with what's remaining, our secondary treatment really does most of the work. We've got about 95 to 98% of the BOD that's entering the secondary treatment should be removed by a this waste activated sludge process. As you're doing this, or as we do this, we often consider what nutrients are there. I think I talked with you guys about this last time, or maybe this was the other class. Depending on what kind of waste you have, it may or may not be limited by nutrients. So I like to give an example. I toured a tissue recycling plant. They had a lot of carbon in their stream, but almost no nitrogen or phosphorus. So that the way they were able to remove their BOD effectively, which BOD is often a good measurement of carbon content. So to remove the BOD that they had, it's like a carbon food source. To remove that, they had to add fertilizer to their bacteria, so that the bacteria would have enough nitrogen and phosphorus to actually make new cells and to grow. So that concept, there's a CNP ratio that kind of describes that concept, where we need about 100 times the carbon compared to about 10, 15, maybe 20 parts nitrogen to 1 part phosphorus. So this would be C, N, and P. This type of ratio is used quite often in oceanography for understanding algae growth. If you have open ocean situations where there's nutrients limiting, then you could maybe seed it with one of the nutrients, and then it'll no longer be limiting, then you get an algae bloom. It's part of that theory. That's where this Redfield ratio comes from. And I think that one's like 100, I think it's 14 to 1, something like that. It's some specific one that happens to correspond to algae. You could look at that to what corresponds to the human body. If you were to kind of totalize the atomic ratios there. And for wastewater, it's just pretty handy to consider that, because in some cases you may have an issue where you need to add one or the other, or perhaps in tertiary treatment you're trying to remove nitrogen, and so you have to make sure make sure that it's not limited in carbon and give it the right conditions so that you get a process that will take nitrogen and kind of consume the majority of it. It's not always the case that you get a perfectly balanced supply of waste to feed the bacteria in such a way that they're just going to remove all the nitrogen and phosphorus and carbon, right? that's not your usual situation. Okay, so I'm going to see if I can. I don't even remember what YouTube this is, so let me. Pardon me just a moment. Let's see what this is. It's probably a wastewater treatment plant. So I think that's the primary effluent coming into the secondary chamber. Actually, that might be a clarifier there, technically on the right. You see on the left, activated sludge. We don't need it that loud. So I think that on the right, it seems like that's a sedimentation basin, and they're collecting the water off the top there at the end of it, so it's just be a rectangular one. And then that water is being fed into the waste-activated sludge chambers here, furious aeration. And if it wasn't already obvious, you don't want to fall into that. But the big reason you don't want to fall into that is because you'll have no buoyancy. So yeah, your eyes go wide there for a second. Like, oh, you literally can't swim in that because of all the bubbles, right? So if you fall into that, if you notice, they'll have ladders in certain spots. And these are not just like 5 feet. They're probably 10, 15 feet deep. So if you were to fall into that, then you need to know the operation of how to walk over to the ladder and climb up. If you needed any extra motivation not to fall into a wastewater plant, right? Pretty horrifying sound. This is in some other country. I don't know where it is. Okay, now you're going to have nightmares. Apologize for that. All of you are now suddenly, thinking of a career change. Okay, so then it's flowing into here. This is probably their second clarifier right here, I would guess. You got a lot of scum at the top. Probably collect that before the discharge. Yeah.
So is those costs where you kind of like deactivation that like sort of nitrogen and phosphorus and stuff, does that happen in like the secondary treatment or is that something?
Okay, so it's a great question about denitrification, whether that happens in the secondary treatment step. A lot of those, there will be some if the conditions allow, and not all treatment plants are built the same. Sometimes you might have anaerobic process first, which will set up the biochemistry and the chemistry a little differently, and then you have aeration. Sometimes you'll go aeration, then aerobic. So I think that there's probably going to be a little bit of denitrification happening in the typical waste-activated sludge like we're showing here, but more likely, if you need a lot of that happening, you probably design a tertiary step specifically to cause the conditions to be ready for that. Now, yeah, and I'd have to go back and look at specifically the steps that you need or the requirements. I think some denitrification will be happening in a activated sludge system. Okay, so I think that's clarified water there that we're seeing. Maybe they're disinfecting in the following chamber or just discharging. But this is now the effluent, and the water looks better, right? That could be a stream or a river with a little bit colored. Definitely not not the same as what we were seeing with all that sludge a moment ago. So I don't really know what level of treatment they're handling, but this looks to me like kind of a small to medium-sized treatment operation. Small municipality, probably. There we go. All right. Okay. All right. So, bacterial growth. When we consider how to find out how much food the bacteria will consume, which is ultimately our goal, primarily, we have to consider what aspects influence their growth. And we do this through this equation called the Monod equation. This is essentially, the mu here is a rate constant. So if we have a growth rate, let's say dx dt equals, if we're talking about some growth of x being our bacteria, we're going to call this mu x, right? That's our growth rate. So this mu is like a k, like a rate constant, right? But like we saw with our flocculation problems, the k in those problems depended on some other variables. So in this case, we're going to have a rate constant mu that's going to depend on some other stuff. So I want to take a moment to explain that. And this will help us understand the relationship between how much substrate, food, waste we have there and the amount of bacteria we've got. So our rate equation, our rate constant, is equal to the mu max, times the substrate concentration divided by this half velocity constant plus the substrate concentration. Okay, mu specifically, we can call it the specific growth rate coefficient. You'll see this is per time. It's a first order rate constant, a growth rate, right? This means that if we have the difference of milligrams VSS per liter over time, we'll say seconds, then the units on the right have to be the same, right? So then X is milligrams VSS per liter. Mu then has to be 1 over seconds, right? Just like we've done in the past, this is first order, this is a growth equation. So that's our K, essentially. And the wording here is specific growth rate coefficient. So given some conditions, those specific conditions, how quickly are they growing? It's a descriptor for that. Now we also have this mu max, which is the maximum specific growth rate coefficient. The mu max is essentially how quickly would they grow if they had everything they could possibly want in the world, right? How fast can they multiply? So if they have all the food, all the right nutrients, and they're not crowded out or anything like that, any weird stuff happening, this is the maximum speed at which they can grow. S, as I mentioned, is the substrate or the food concentration. That's milligrams BUD per liter. And then X, of course, is our microbe concentration. That leaves us with Ks. This is called the half velocity constant. It's the value of S, the food, when the specific growth rate is half of its max. So I'll explain that graphically in a moment. It's just sort of a description of at what point in the food, like if you go from zero food to all the food they could want, where on that spectrum are they growing half as fast as they could? So they have half the amount of food that they want, sort of. Okay, so with those in mind, let's take a look at how that specific growth rate coefficient would change with food. So As you add food, it's typically going to be going up, and then eventually it will level off and you'll reach your mu max. So at some point, you're at a maximum, you'll reach that asymptote. That'll be our mu max. And so then if we just say, okay, well, halfway point between this and 0 would be something like here. So we could say that's 1/2 mu max. And if we then draw a line over here and then down from there, this value is the Ks. So that's just sort of a visualization of how that works in terms of what we're talking about here. So this growth rate, this specific growth rate coefficient is equal to the fastest it can go multiplied by the amount of food we have divided by the amount of food we have plus the amount where it's growing half as fast as it could. So that's just the equation we have. It tends to model or predict pretty well how fast bacteria will grow. So if you think about that